this is it. This is our last day of new material to cover because next week, Tuesday and Wednesday, we're going to be just doing review before our final on Thursday. So things that I want to do today, examples of SN1 and SN2 on alkyl halides, reactions with alcohols, which is going to feel like a review of reactions with alkyl halides, except a little bit easier and a little bit different. And then also a reaction called the Diels-Alder, which those of you in lab this week, you've seen it or are seeing it tonight. It's not as hard as it seems, but I remember when I learned it in college, feels like magic, a little bit of witchcraft, and it's actually super easy to predict as long as you understand what you're looking at. So let's kick off with examples of SN1 and SN2 on alkyl halides. Now, I'm not going to put that table back up. A lot of you asked me yesterday, should I try and make my table of reactions where I've been putting alkenes and alkynes, should I try to make that include these reactions with alkyl halides? My answer to that would be maybe. The challenge about alkyl halides is that there's a lot of different regiochemistry. Is it a methyl? Is it a primary? Is it a secondary or tertiary alkyl halide? That changes a lot. Are you going to have an example for each of those? Maybe, not a bad idea. And then the reagents that you add can change a lot. Are you going to show strong base, strong nuke, weak base, weak nuke? How are you going to tie in the fact that some regiochemistries with some reagents can give two different products? That's a challenge. My advice would actually be to just use that table that we crafted yesterday to recognize and review substitution and elimination with alkyl halides, rather than trying to incorporate it into a larger table of reactions. Get to know that table and learn how to use it as a map. Look at your regiochemistry, look at your type of reagent. So let's take this secondary alkyl halide. True or false, that is a benzylic alkyl halide. False? Is it attached on the carbon adjacent to the ring, to the aromatic ring? It's too far. This position is benzylic. This position is not. But what do we know about benzylic positions? They stabilize radicals, they stabilize positive charges, and they stabilize reaction intermediates as well. So when I react this alkyl halide with water, and I look for the substitution product that I get, I actually get this alcohol. Water is a precursor to an alcohol product. That's not new for us. When we looked at alkene addition reactions, the halohydrin X2 in water was a precursor to an alcohol product. What's happening here is a structural rearrangement, which tells you what? Carbocation intermediate. If there's a carbocation intermediate, what type of mechanism is happening? First order substitution or second order substitution? Second order does not have a carbocation. First order creates a carbocation that can rearrange. There is a byproduct here. Can you guys see what the byproduct is? HBr. One of the hydrogens from water is gone, and the bromine has left. I will ask you to know mechanisms for SN1 and E1, SN2 and E2. We've already looked at the E1 and E2 mechanisms. The SN1 and SN2 mechanisms are very similar. I'm going to abbreviate this aromatic ring in my mechanism as pH. There's nothing meaningful about the double bonds. There's nothing meaningful happening in the ring. But it isn't meaningful to know that the position next to it is benzylic. First step. Leaving group leaves. This is the same as our first step for what other mechanism? Sorry, I wanted to clarify. This is SN1. This was the same step for the E1 mechanism. And one other thing, I need to have my water here. It doesn't play a role yet, but I like to keep everything present. Leaving group leaves. When bromine kicks off, it creates bromide and leaves behind a carbocation. Carbocations don't form easily, but polar protic solvents like water, they can actually stabilize that positive charge through a donation from that partial negative on the water. Step 1A, because not every SN1 reaction has this, but this SN1 reaction does, we'll see a carbocation rearrangement. So I'm explicitly drawing in one of my benzylic hydrogens. There are two, only one of them is relevant. That hydrogen takes its electrons over, satisfies the carbocation on the right, but leaves behind a carbocation on the left. Step 2 is where we have a nucleophilic attack. My new highly stabilized benzylic carbocation accepts electrons from water. Let me know when you see the mistake. There is stereochemistry. There's also stereochemistry here, and it wasn't made obvious to us, so we're just not paying attention to it right now.
Okay.
But it would be racemic. Actually, if that means anything to you here, we should say it here. This makes a racemic mixture, 50-50 of the two possible enantiomers.
And if we were to draw it with the alcohol being wedged to the top.
Don't know whether it attacks from the top or the bottom. Stereochemistry is not shown.
Would it still be H2O, but the Br takes hydrogen?
So it's not just H2O, it's H2O plus. So these two hydrogens are still present, and now that oxygen has a positive charge. And then in the last step, Nuyura, you had it right, deprotonation. But this is not deprotonation like we saw in elimination. This is deprotonation of the alcohol. So I'm going to explicitly show at least one of its two OH bonds. I know some people that like to show both of them. That's great. And bromide here can act as our base. and it gives us our alcohol product plus HBr. I want you guys to remember that by doing your mechanisms this way, you're literally doing twice as much work. Because every intermediate you draw, you are redrawing to show it reacting in the next step. If you don't like this, you can show your mechanisms more like this. And then I'm going to have to come over here. Each of these steps feeds directly into the next step. That's half as much work because you don't have to redraw everything, but it's twice as cluttered because every time you draw something, you've got to draw arrows on it. And that can just make it messier. So please do what works best for you. If you want to practice doing both, do it. One thing that I don't want to see is you guys trying to reinvent the wheel on these mechanisms. What that means is water cannot attack while bromine is leaving. Especially water cannot attack the carbon that it's attacking while bromine is leaving, because in this case, there's a carbocation rearrangement. So you can't combine these steps. You can't show the leaving group leaving, the hydride shift, and the nucleophilic attack all at once, because that is not a first order reaction mechanism. So I'm giving you these to you step by step, and I'm giving you the names because that is what's happening. You don't have to show it step by step. You can show it sequentially like this, but it still needs to include all of those individual steps. All right. Example 2. Hayden, what I'll do for you this time is actually throw in some stereochemistry because it does become relevant when we look at it here. Same starting material, but this time I am showing the chiral center. I've got two things written over this arrow. One of them is more important than the other in terms of reactivity. This is meth oxide. It's not oxide because it's not O2 minus. It's oxide bonded to a methyl group. Meth oxide is what type of reagent? How is it as a base? Strong or weak? We consider it strong. How is it as a nucleophile? Strong or weak? Strong. This is methanol. How is this as a reagent? It's not really an acid, but it can be considered a weak acid. It can also be considered a weak base. Is it a strong base or a weak base? Weak base. Is it a strong nucleophile or weak nucleophile? Weak nucleophile. So in a reaction where both of these reagents are present, who's going to get the job done? A strong nucleophile or a weak nucleophile? Something that's good at its job is going to do the job. I get this a lot where students say, I have both of these. How do I decide which one reacts? Okay, well, I've got a really lazy employee and I've got a really motivated employee. How am I going to decide who gets the work done? Strong nucleophile drives the reaction. What happened to the stereochemistry at my chiral center? Inverted. It went from one configuration to another. Here's priority 1, 2, 3. That's an R configuration. And here's priority 1, 2, 3, but it's backwards. That's an S configuration. My R chiral center became an S chiral center. You guys are going to hate this mechanism, so I apologize for that. This is classified as what type of reaction? It is substitution. It's also nucleophilic. Second order, SN2. In my mechanism, first step, backside attack. And I apologize for this in advance. I know you guys have worked hard all semester. This might just feel like the end of it. Nucleophile bonds to the alpha carbon. Leaving group leaves. And I get my final product. Okay. It's the hardest one you've seen yet. Most classes teach substitution and elimination as some of the first reactions and some of the first mechanisms. You're learning it as your last mechanism. How does it compare? Easier? It's just 2 arrows, 1 step. It's even easier than E2. E2 has 3 arrows and there's a lot of different atoms involved. This involves the nucleophile, the electrophile, and the leaving group, and that's it. Now, I do want to demonstrate why this gives us inversion of stereochemistry. The more time you spend on this, the more familiar I think it will become to you. It does have to do with molecular orbital theory. In order to break the CBr bond, the oxygen needs to occupy the sigma star orbital. And the sigma star orbital is linear to the sigma orbital. So in order to occupy it, the nucleophile needs to come in from exactly opposite. If we were to look at that backside attack, ChemTube 3D, we're just going down under organic reactions. This is it. It attacks directly opposite. A lot of people describe what's going on here at that electrophilic carbon as kind of an umbrella opening. You guys ever had your umbrella get pulled by the wind? And instead of being a cone down, it becomes a cone up? We would say that is kind of similar to inversion of stereochemistry. And that's similar to what's happening here. These 3 other groups are changing their orientation. So if what's leaving is coming towards you, then what's substituting will be going away. The hydrogen that was going away is being shoved forward so that it looks like it's coming towards you. So now I want to give you this orientation that looks similar to what we see on the board right now. It's not super easy to see it, but these 2 hydrogens on the left, these are in plane, like the plane of the board. This is your leaving group. It's coming towards you. This hydrogen right now is going away. But after the substitution, the hydrogen is coming towards you, and the new nucleophile is pointed away. If that doesn't seem obvious to you now, go home and pull up ChemTube 3D. Go find this simple SN2. Arrange it like what you see on the board, and watch how that hydrogen pushes away from you and towards you during the reaction. Oh, wow. Well, that does it too.
How come the beta hydrogen doesn't move compared to
there's no carbocation rearrangements because no carbocation forms. Here, a leaving group leaves, creating a vacancy on the carbon. That carbocation is actually more stable only at the adjacent position. And so this hydrogen shifts over, leaving behind a more stable carbocation. But here there's no carbocation to form. That carbon never loses a bond. It substitutes a bond at the same time that it loses a bond.
What makes that SN2 exactly?
If you increase the concentration of nucleophile, you get more product faster. If you increase the concentration of electrophile, you get more product faster. The rate depends on the concentration of both of them. Second order. It's substitution because you substitute one bond for another, and it's nucleophilic because a nucleophile drives the substitution. That's what makes it SN2. Do you guys remember talking about transition states? Which are not structures that can be isolated, but they are the depiction of bonds breaking and bonds forming. There's only one transition state here. And it depicts the leaving group leaving and the nucleophile coming in. Do you know whether that CO bond is forming or breaking? You can't know at a transition state because it is a tipping point. If a molecule of solvent runs into this, it could shove it the wrong direction and not actually complete the reaction. There's a transition state for E2 as well. If we were to look at the elimination product that forms in this reaction, in elimination, E2, a base bonds with a beta hydrogen, breaking the CH bond, while the carbon-carbon double bond forms, which needs the leaving group to leave. There's a lot more steps going on here in E2 compared to SN2. Would you agree? And this lies the issue with substitution and elimination. The same reagent can give a substitution product or an elimination product at certain carbon substitutions. So this leads us to temperature control. Anywhere on that table that we generated yesterday, where a reagent reacts with a specific substitution to give either substitution or elimination, we can actually control the temperature of that reaction to promote either substitution or elimination. Adding heat, which we often give as delta, promotes elimination products. Removing heat, which we often describe as low temperature, promotes substitution products. So let's take bromomethylcyclohexane. And we're going to show what products form in 3 different conditions. First, let's look at when bromomethylcyclohexane reacts with tert butoxide. No temperature indicated. Then let's see what happens when it reacts with tert butoxide and heat, or tert butoxide and low temperature. Tert butoxide is an interesting reagent because even at primary alkyl halides, it's so bulky, it has a hard time running substitution. So it has this competition. Will it substitute the carbon or will it eliminate? With no temperature indicated, we have to predict that both products are possible. Tert butoxide acts as a base, gives me an elimination product. I know that feels like a weird elimination product, but keep in mind that this primary alkyl halide only has 1 beta hydrogen position. There's only 1 elimination that can form, whether or not it looks like the least substituted, because tert butoxide often does anti-Zaitsev elimination. If it substitutes, I want you to keep in mind that it is oxygen that acts as the nucleophile. Just like here, where oxygen acts as the nucleophile, or here, where oxygen acts as the nucleophile. So instead of being a carbon-bromine bond, I get a carbon-oxygen bond, and that oxygen creates an ether, a tert butoxy ether. At high temperatures, the elimination product is preferred. What is the byproducts that form when tert butoxide eliminates this primary alcohol, or this primary alkyl halide? Bromide is kicked off, and tert butyl alcohol is formed. The conjugate acid of an alkoxy is an alcohol. So what product do we get if we run this at low temperatures? Just the SN2 product. This is what is promoted in the reaction. If you don't want to see it as OTBU, we can draw out that tert butyl group here and clearly demonstrate the ether that's formed. All right, let's do some practice. I want you to predict the starting material that can lead to each of these products. And I want you to provide reagents that can give me these last two reactions. This is a line, by the way. I just don't want that to be confusing. That's an O with a line. You could put OCH3. No. Yes. And we don't have to say this here, but it doesn't hurt. No, down here.
No.
Yeah. Mm-hmm. If you guys want to talk with each other, please feel free to. What do you recognize that's happening? What information can you pull out from this? This will do this. Where? Maybe, yeah. This is something that is going to come up with. Elimination. Great. Great starting material. Yep. You're really close here, but that's not going to give us this product. Neither will this, neither will that. Because of its strength.
Isn't it just a CH3O minus?
Where does CH3O minus fall in our table? Strong base, strong nuke. Weak base, strong nuke. Strong base, weak nuke. Look at the table if you have it. All right, I want you guys to turn and talk to each other. What have you figured out in this time? What are you recognizing? What are you stumbling over? What doesn't make sense?
So you just put that.
Yeah, I didn't know what. Yeah, because that's a weak base strong.
Oh, for that. And then he said, SMR, he wants, I said, you're right. So then I thought, okay, well,
Yeah, the starting material is great.
I really just I have no idea.
So you know part of it.
I only got to the first one.
Yeah, I probably got that.
CH3O minus.
Figured out that that's elimination and that's
You would
the
get
carbon
something like
counter.
this.
One.
Where it's
That
dashed,
was substitute.
which will say it'll say OC.
So it's
Not
The bond is
something with.
And And
It's
so
just
then
with adding heat.
Because it's weak,
substituted.
it's going to promote it.
I thought that was SE2. In E2.
So I'm just looking at it, I knew there was a carbon counted intermediate. But I had
Well, the reagent you provided won't allow for one.
I could just make it happen.
And then you did the right thing. No,
I'm just kidding.
it's too strong.
It's,
You need to rearrange it. This doesn't allow for rearrangement. What would? This does give you the group you want, but it doesn't give you rearrangement. So how can you get that same group and allow for rearrangement? Add an H, yeah, make it a weak nucleotide. Instead of strong.
It would be SN2 or so to make sure that it's
that's what I was thinking, right, because it's secondary.
Cyanide's not going to be involved. Well, we need that
So, the only one that prefers E2 is the two.
Yeah, because it could make two different.
No, OH this is a good starting material, but OH minus gives us Zaitsev elimination, not
Yeah.
You're not talking to anything?
No, we are, it could be.
Oh.
Strong
This won't work because it doesn't give a
Yeah.
And this won't work because it
Yeah, that's what I was
knows
thinking, some would be right now, could also be different factors.
The first part of
for the last one,
this class, I was like,
what's your question?
This is the small bases.
OH minus won't get and you need it on Z. Yeah.
They still undergo E2.
OH minus is starts here. OH minus. But what is indicated here? We have to show series of zeros and numbers. What if you add children?
So then I guess they could go.
And this one down here. This is a good string, but that would be a low range, not no C.
Huh?
So you want something that's lower string? I don't see low in here, that's just TBU.
Yeah, a lot of it's today, so.
There you go. And that has 3 methods in here, not
Yeah,
just that. And it doesn't allow for rearrangement. All right, guys, let's pull it back together. The most important thing here in solving this synthesis is first being able to figure out what this all comes from. So you need to look at the cyanide that gives this product in order to be able to figure out what the other ones are starting from and what you'll need for that. Cyanide is what type of reagent? Strong base, strong nuke. Strong nuke, weak base. Strong base, weak nuke, or weak nuke, weak base. Weak base, strong nuke. On a secondary carbon, this runs what type of reaction? Only SN2, which means there's no rearrangements, but there is inversion of stereochemistry. So the cyanide carbon, the carbon attached to cyanide, is going to be the carbon attached to my leaving group. I can make it whatever I want. I'm going to make it Cl. And that Cl needs to be kicked off opposite of how my cyanide is added on. Cyanide is dashed, so the leaving group must be wedged. That's the only starting material. Okay, substitute any halogen in there. That's the only starting material that gives this product. Now I know that this elimination can be described as what? Zaitsev or anti-Zaitsev? My leaving group has a primary beta and a tertiary beta carbon. I'm eliminating at the primary, less substituted, less stable, anti-Zaitsev. What is the only base that will give me my anti-Zaitsev product? Tert butoxide. Do I need to provide heat here to promote that elimination product? At a secondary alkyl halide, terp-butoxide experiences too much steric strain to act as a nucleophile. It's only going to give elimination. But if you want to provide heat, is that going to change the product? No.
Is people the only one that for everybody?
If you add hydroxide, it gives you this product. The Zaitsev elimination. If you add methoxide, ethoxide, if you add water and heat, if you add methanol and heat, any other base, strong or weak, is going to give you the Zaitsev elimination. Terp-butoxide is the only one that gives us this anti-Zaitsev. Now my last one. Structural rearrangement or no? There is. Substitution or elimination? So up here I had an SN2 reaction. Down here I had an E2 reaction. What kind of reaction am I looking at in my third reaction? SN1, which tells me that at a secondary alkyl halide, I need a specific type of reagent. Cannot be a strong base, strong nuke. Cannot be a strong base, weak nuke. Cannot be a strong nuke, weak base. It must be a weak base, weak nucleophile. Weak bases, weak nucleophiles at secondary carbons, they compete. A carbocation forms, and then that reagent isn't good at being a nucleophile, but isn't good at being a base either. So both things can happen. How do I make sure that I promote substitution? Good. I need to run this reaction at low temperature. And I need a reagent that gives me oxygen with a methyl group. If you added water, where's the methyl coming from? If you added terp-butoxide, where are the extra methyl groups going? What I need is something that has CH3 and O, and I want to control its strength. Do I make this CH3O minus, or do I make it CH3OH? CH3O minus is strong nucleophile. That would give me something similar to SN2. I need CH3OH, which is a weak nucleophile. That will let me run my SN1. Pop quiz. How do I make this product? Sorry? Cl minus from what? How about from an alkene addition reaction? How could I make this? HX addition could work. If I have this alkene, will adding HCl give me this product? What you're doing right now is running through the regiochemistry of HX addition. It's Markovnikov. So H adds here, Cl adds here. Not the product I want. If I have this alkene, can I do HCl addition? Once again, you're thinking about the regiochemistry. I get a carbocation that forms here. That carbocation rearranges to the tertiary position. I still add the chlorine at the wrong spot. One more time. Oh, Cl2 is not going to work because that adds 2 chlorines. I'm actually going to take this reagent, and I'm going to add HCl and hydrogen peroxide. What reaction is that? Radical HX addition, also known as anti-Markovnikov HX addition. This provides the radicals. The chlorine adds first. The carbon radical also forms and takes the hydrogen last. This is the only way to get that starting material based on what we've seen so far. All right, I just want to point out a couple of things about my example. I want you to feel comfortable swapping cyanide for azide, for sulfide, RS minus, HS minus. I don't have to control the temperature here because those strong nucleophiles that are weak bases, they're really only going to give me SN2. I don't have to worry about elimination from a weak base. All right. Good application of temperature control, regiochemistry, and type of reaction happening. In my opinion, SN2 products should almost always be the easiest because you're just looking at an inversion of stereochemistry, and whatever group you've got there just attaches where your halogen was. It's much less common, but you can actually substitute an alkyl halide for a different alkyl halide. You could add iodide to this reaction, and you would get an alkyl iodide instead of an alkyl chloride. There's not much purpose for it. There's not a lot of need for it in organic synthesis. There's another conversation to be had here about the type of solvent. It's not something that I spend as much time on because, once again, it doesn't come into play later in organic synthesis. But if you are running SN2 reactions in polar protic solvents, it can slow down your nucleophile. If you run this in water or ethanol or acetic acid, it can start strongly bonding with your nucleophile and slow it down. You run these reactions in polar aprotic, acetone, DMSO, THF, any sort of ether. They still dissolve your nucleophile, but they don't hold it back quite as much. They don't solvate it quite as strongly, so they can allow it to run. I focus a lot less on the solvent because that's more of a physical organic chemistry approach, explaining rates and kinetics and nucleophilic strengths. I want you to focus a little bit more on synthesis, conversion of functional groups, paying attention to where your carbons are. All right, any questions before we move on? I have a question for you. Do we need to cover how to name alcohols? Are alcohols a higher priority or lower priority than alkenes in terms of locant numbering? Alcohols are higher. Do alcohols take on the suffix or the suffix stopper? Suffix stopper, which means you can have an ane-all, an alkane alcohol. You can have an ene-all. You can have an ine-all, and you can have an ene-ine-all. But no matter what, you're prioritizing the placement of the alcohol first, and then you're looking at wherever everything else falls. Okay, I'm glad because I didn't want to have to spend too much time on nomenclature of alcohols today. Our reactions with alcohols look very similar to our reactions with alkyl halides with some differences. First, we can run elimination in acidic conditions. I think we've already seen this generic example where we take an alcohol and its beta hydrogen and we provide acid to create an alkene. Unlike alkyl halides, alcohols are not useful in the synthesis of alkynes. Now, there is an important thing about this acid. You might see this written as H+, which is generic acid. You might see it written as H2SO4. Those of us in lab this week, or this semester, we also used phosphoric acid, H3PO4. But you do not want to use HCl or HBr or HI. You can think of those hydrogen halide acids as being nucleophilic. They have Cl minus, Br minus, I minus, which might actually substitute the alcohol. But H2SO4 is non-nucleophilic. Acetic acid would be better than hydrochloric acid, but given that sulfuric acid is cheap and easy to get your hands on, most people use sulfuric acid. These are almost always E1 mechanisms. So if I take this 2,3-dimethyl cyclohexanol and I react this with sulfuric acid, I cannot just look for the Zaitsev alkene. I have to pay attention to possible carbocation rearrangements and then the Zaitsev alkene. The carbocation that forms here rearranges to a tertiary carbocation. And that tertiary carbocation can be eliminated into 1,2-dimethyl cyclohexene.
So I thought hydrosulfuric acid was a strong acid.
It is.
Oh, E1, I was thinking acid.
Yes, sulfuric acid will not substitute, ever. Another word for elimination of alcohols is dehydration, and you can see why. We produce an equivalence of water in this reaction. Now, the mechanism is not something that I will ask you to show me on an exam, but it is not because it is more challenging. In fact, what I'm going to give you are just the steps. In acidic conditions, the first thing that always happens is protonation. The acid protonates something. What would be the base in this reaction? The alcohol. So the first step is to get an alcohol. That's basically water attached to a molecule. The second step is that your leaving group leaves. Or in other words, your carbocation forms. And then, of course, in those cases where we have E1 elimination, we can see carbocation rearrangements. So you could say 1A, carbocation rearrangement. And the last step is as simple as deprotonation. That's where the carbon has its hydrogen removed. The carbon is deprotonated, and it gives us the alkene. So here's a bit of a challenge. The alcohol reacts in acid to make alkene and water, but alkenes and water react in acid to give alcohols. We saw that with one of our first alkene addition reactions. So in reactions like this, the equilibrium has to be overcome. When we were in lab, we overcame equilibrium by distilling the product as it formed so that it couldn't reverse itself back into the alcohol. Same thing here, we would need to try and make sure that in making the alkene, we don't allow it to react with that water and acid to go through hydration. Now, one of the reasons that we can't use HCl, HBr, and HI is because alcohols can also be substituted in acid. This is where the acid is an HX reagent. So in my generic example, I've got this alcohol, reacts with HX, and at the end, I get an alkyl halide. There's a bit of an equilibrium issue here too, because we literally just saw that water can react with alkyl halides to give us alcohols. These reactions are reversible as well. And these are nearly always SN1 reactions. And it's for the same reason. In acidic conditions, the alcohol gets protonated and becomes this good leaving group as water, which dissociates into a carbocation. And when I say nearly always, I mean methanol cannot go through SN1. That carbocation is too unstable. So methanol goes through SN2. Primary carbons have a very challenging time forming a carbocation. So primary carbons almost always go through SN2. So let's take an example here. Those of you that took lab this semester will remember the synthesis of 1-bromobutane from 1-butanol. No, the top one is 1-bromobutane. The bottom one is not 1-chlorobutane. What?
I looked at the wrong.
Okay, yeah, that makes sense. What type of reaction mechanism is proceeding to take 1-butanol and make 1-bromobutane? SN1 or SN2? SN2. If it were SN1, a primary carbocation would form adjacent to a secondary carbon, which would result in a carbocation rearrangement. And that would leave us with 2-bromobutane, not 1-bromobutane. So this mechanism must proceed by SN2. I said nearly always. Primary and methyl carbons are exempt. HCl on this 3-methyl 2-butanal. Can you predict the product? Chlorine adds to the tertiary carbon. Chlorine replaces the oxygen right here. So I'm going to draw the two possible products that I think I'm hearing from the class. Oops. Yeah, that doesn't make a lot of sense. Sorry. First step, protonation. Second step, carbocation formation. Because this is a secondary carbon, carbocations are supported here. That secondary carbocation is adjacent to a tertiary carbon. So step 2A, carbocation rearrangement. Then step 3, nucleophilic attack from chloride. This product is isolated, and this is not.
Could you explain why that can form a carbocation? Because HCl is a strong acid.
HCl is a strong acid, so HCl protonates the alcohol. That basically makes it water attached to the carbon. And that water dissociates from the carbon, which leaves behind a carbocation. What's left over after HCl protonates this is Cl minus, a nucleophile that can substitute or do nucleophilic attack. Yeah? Did that answer it? What if I don't want carbocation rearrangements? Oftentimes, I hear this referred to as inorganic reagents. Acids are also inorganic. These acids anyways, HCl, HBr, those are inorganic reagents. But this is a common way to think of it. There's two very common reagents that are used. And what I'm actually going to do here is highlight the stereochemistry of my alcohol to demonstrate how these two reactions work. If I have R3-methyl-2-butanol, and I react it with thionyl chloride, that's SOCl2. Thionyl chloride actually accepts electrons from the alcohol, breaks off one of the chlorines, and then that chlorine substitutes the alcohol directly. No carbocation forms, no rearrangements occur, and inversion of stereochemistry. That essentially makes it what? SN2 substitution. So it's challenging to substitute the alcohol for SN1, for SN2 in acidic conditions. But with these inorganic reagents, we can give that SN2. The other reagent is phosphorus tribromide, PBr3. This gives a very similar result, except that it gives us an alkyl bromide instead of an alkyl chloride. I want to point something out about substitution of alcohols. Our other nucleophiles will not substitute alcohols the way that they will substitute alkyl halides. And that's because of the acidity of the alcohol. If I take this primary alcohol, where SN2 is typically pretty favored, I just get this equilibrium of acid-base chemistry. And quite honestly, the equilibrium lies heavier towards the alcohol side, but that CO bond doesn't break the way that a CX bond would break. That's why alcohols have to become protonated in order to kick off. Or the alcohol has to bond to a sulfur or a phosphorus in order to get kicked off. So these other reagents don't work. But what does work is first substituting the alcohol for an alkyl halide. I could use HCl here. I could use SOCl2. And then providing our nucleophile. Multi-step synthesis. Substitute the alcohol for a better leaving group, then do substitution.
Well, would you ever want to react like sodium amide? Like THF?
Well, sodium amide is going to give you that same issue with the alcohol of deprotonation.
So just taking the intermediary step?
So substitute for an alkyl halide and then add amide. The problem is that sodium amide is such a good base that it often just leads to elimination. So it can be hard to do substitution with sodium amide. At least I hear. I've never worked with it. Does this make sense? Alcohols do not react like alkyl halides do. And so oftentimes we need to substitute the alcohol for an alkyl halide. And now we have different ways of doing it. If we're all right with SN1, if we're all right with carbocation rearrangements, we can substitute an HX. If we can't afford carbocation rearrangements, or we need our stereochemistry to be specific, we can use these inorganic reagents. Now this last one is very similar to substitution, but I call this transformation of our alcohols. You can also refer to this as sulfonation. A sulfonyl group or a sulfonate group, it can have a few different forms, but it's usually this R-SO3R group. It looks a little bit like sulfuric acid, H2SO4, except that there's a carbon-sulfur bond. There's a few different reagents that can be used here as well. We're going to focus primarily on this one, tosyl chloride, TSCl. And we're going to abbreviate it as TSCl so that you guys don't have to draw this structure. That is p-toluene sulfonyl chloride, otherwise nicknamed tosyl chloride. And honestly, please don't draw it. I mean, put it in your notes if you'd like to, but on paper, please don't draw it out. It's just so messy to draw. So I want you to keep in mind, TS, Cl, here's the Cl group. So what constitutes TS? From the sulfur all the way back. That's going to be our main reagent. But there are a few other members of this family. If you're working in a lab and you need to do a certain solvent, you need to control solubility, or you have certain acid or base properties, you need to control electronics. You can also work with triple chloride, TFCl, or you can work with mesyl chloride, MsCl. They're just different versions of a sulfonyl group. The R group on the left-hand side is just a little bit different. The generic reaction here,
Oh, it's done. I got it.
thank you. Just gonna make sure it's pointed the right way. The generic reaction that we're gonna see for these, and I'm actually gonna put some stereochemistry in this. This is not so much substituting the alcohol, even though there is no alcohol left over, as it is transforming the alcohol. Why? Because the bond to oxygen never breaks. The COH becomes COTS. I don't have an alcohol anymore. I have a sulfonyl group, which means it behaves differently from alcohols. A lot of people refer to this as a pseudo halide. What are they trying to get across there? It reacts like a halide despite it not being a halide. What's the byproduct of this reaction? HCl. Is this SN1 or SN2? Trick question. It's not. You're not substituting the carbon. So it's not SN1 or SN2. This is transformation of an alcohol. Got ya. If anything, this would be like sulfonyl substitution, which despite potentially being first order or second order, wouldn't be classified as SN1 or SN2. I don't know if I said this, but SN1 and SN2 are bad names. It's just what the textbook's like. All right. Here's an application of all of this. Let's say that I have this alcohol starting material. And I want to get to this thiol product. Notice the stereochemistry of the reaction. I want my alcohol to start wedged, and I want my thiol to be dashed. So the stereochemistry is important. Well, alcohols cannot be substituted by thiols. There's just an acid-base equilibrium that happens between the S- and the OH. So I'll transform it. If I transform this with HCl, this occurs via SN1, and I get a mixture of stereochemistries, a racemic mixture of enantiomers. Is that useful in getting to this one stereoisomer thiol? No. So this is not my best route. If I use SOCl2, or I use that a little too often. Let's use PBr3. Does the same thing, just changes the nature of our halogen. Okay, now I get one selective stereoisomer, the dashed halogen. Can I substitute this dashed halogen for this dashed thiol? What reagent would I need to add? SH-. when SH minus acts as a nucleophile on this secondary carbon, does it run SN1 or SN2? Gives SN2, which gives inversion of stereochemistry. That would give me a wedged thiol from my dashed alkyl halide. Does that work? Bad route. It doesn't give me the stereoisomer I'm looking for. So what I do instead is I transform that alcohol without changing its chirality. TSCl gives me a wedged tosyl group. And now that can act like a halogen and go through SN2 substitution, inversion of stereochemistry with SH minus. So there can be a usefulness for all of these different reactions. HX substitution, maybe you need to take advantage of structural rearrangement. Inorganic substitution, maybe you do need to control that stereochemistry. And alcohol transformation, maybe you want to preserve that stereochemistry for as long as possible. They all give very similar results, but they get there in a very different way, and they have slight nuances to the stereochemistry of the final product. So alcohols can be eliminated, substituted, or transformed. The only thing that we haven't really said about alcohols here is that they can be the nucleophile. And I'm just going to say this very quickly. Here I have one propanol reacting with one bromopropane to give me dipropyl ether. Not bad. Or here's another idea. Here I have 4-bromo-1-butene and I'm putting it through hydroboration oxidation. At first, this gives me 4-bromo-1-butanol. But 4-bromo-1-butanol can react with itself through an intramolecular reaction. And I can make THF, tetrahydrofurane. That's where the alcohol on carbon 1 substitutes the bromine that I'm calling here carbon 2. So we've already seen this. We saw alcohols act as nucleophiles in the halo ether addition reactions. We saw alcohols act as nucleophiles in SN1 or SN2 with alkyl halides. It's good stuff. Okay. Our last reaction This is like a whole new class. This one is named after two guys, Diels-Alder. And not a lot of reactions that are named have super useful descriptive names, but this one actually does. This is a 4+2 cycloaddition. And I want to break this down. The reagent that brings 4 atoms is a diene. But that's not just any diene. Those 2 alkenes have an uninterrupted series of p orbitals. What word can we use to describe an uninterrupted series of p orbitals? Conjugated. This is a conjugated diene. If we looked at MO theory, guess what? There is a pi bond that spans all 4 atoms, not a pi bond between atoms 1 and 2 and 3 and 4. That means that this conjugated diene behaves a very specific way. And this diene, this conjugated diene, is separated by a single bond. And you can rotate around single bonds. So this is referred to as the S-cis conformation of the diene. Relative to the sigma bond, the diene is cis. There is a lower energy conformation of these conjugated dienes that is unreactive, and it's called S-trans. We require our conjugated dienes to be in the S-cis conformation in order for Diels-Alder to happen. We're going to label those atoms in the conjugated diene as 1 through 4. Oh, thank you guys. The 2 other atoms come from a reagent that likes to react with the diene, the dienophile. In its simplest, the dienophile is just 2 carbons with a pi bond. That could be an alkene or an alkyne. And these give us atoms 5 and 6. Oftentimes, I'm going to demonstrate that you can have this be an alkyne as well. Oftentimes, these dienophiles have substituents that we refer to as electron withdrawing groups. These are typically conjugated. They have an uninterrupted series of pi orbitals. They're conjugated to the dienophile, and they have electronegative atoms that pull electron density away. So we abbreviate that as EWG, electron withdrawing group. That's a carbonyl, a nitrile. Those are the most common substituents. And like the name says, this cycloaddition gives us a ring in the product. A ring with size 4+2. One of the pi bonds is consumed in the reaction, and one of the pi bonds transforms into a ring. So there's a degree of unsaturation consumed, but there's a degree of unsaturation transformed from a pi bond to a ring. So this is your template, the simplest Diels-Alder product. Every Diels-Alder product has this cyclohexene template. I want to give you guys some examples. I'm not going to ask you to show the mechanism here, but the mechanism is actually pretty simple. Carbon 4 bonds to carbon 5. Carbon 6 bonds to carbon 1. And the pi bond from 1 and 2 relocates between 2 and 3. It's really cool. If you look at the molecular orbitals for that diene, you can actually see why the pi bond exists between 2 and 3. There's a molecular orbital that suggests that would exist. Stereochemistry on the dienophile is conserved in the Diels-Alder reaction. So a cis alkene gives a syn Diels-Alder product. A trans alkene gives an anti Diels-Alder product. So I'm going to take this 1,2-dimethylene cyclohexane. That's basically just the diene that I have here, but then carbons 2 and 3 are connected by a series of atoms in that ring. And if I number them, I've got 1, 2, 3, 4. And then I'm going to react this with this cis dialdehyde alkene. On the alkene, the two aldehydes are coming off of the same face. The alkene is carbons 5 and 6. I had one 6-membered ring. I made a new 6-membered ring. I'm going to map my carbons. The pi bond goes between carbons 2 and 3. Carbons 5 and 6 are now chiral. And these groups have the same stereochemistry because they came cis on the alkene, they end up syn on the product. There's a lot of information to dive into here in terms of the energy of the products, kinetic, thermodynamic, endo, and exo products. We're not going to get into that too much. I also want to give you an example with an alkyne. We're going to start this reaction with cyclopentadiene. And our cyclopentadiene reacts with this 1,2-dicyanoacetylene. The diene gives me atoms 1 through 4. The dienophile gives me atoms 5 and 6. I'm going to have a 6-membered ring in my product, always, with a double bond between atoms 2 and 3. But atoms 1 and 4 are connected by a 5th atom. So in the product, atoms 1 and 4 must be connected by a fifth atom. Now I haven't drawn that very well because it looks just like a straight line. I'm going to have it come at more of a bend so that I can see that there is another atom there. That's a bicyclic structure. That's a ring within a ring. 5 and 6 consumed one pi bond, but leave behind one pi bond. The acetylene uses up one of its 2 pi bonds, leaves behind the other, and the cyanides are still attached. Planar, flat, achiral carbons. No wedges or dashes like we saw before, because here I went from trigonal planar to tetrahedral, but now I'm going from linear to trigonal planar. The last thing that I want you guys to see is how to reverse one of these to figure out the starting materials. That looks like a fairly complicated structure. So there's a lot going on. It's 2 rings fused together by an alkene. There's 2 chiral carbons with carboxylic acid groups coming off of them. But can I map the carbons 1 through 6 onto this Diels-Alder product? The easiest places to find are atoms 2 and 3 and 5 and 6. 5 and 6 often have the electron withdrawing groups on them, and sometimes a double bond. 2 and 3 often just have a double bond. 1, 2, 3, 4, 5, 6. So to separate this, I need 5 and 6 to be its own reagent, and I need 1 through 4 to be its own reagent. The diene has double bonds at 1, 2, and 3, 4. The dienophile gets an extra pi bond between 5 and 6. That makes it a double bond. And given that my stereochemistry of the 2 carboxylic acids is anti-trans to each other, the alkene that produced it must have been a trans alkene. Stereochemistry of the precursor enforces stereochemistry of the product. That's actually not new to us. We learned about that in our stereo-specific elimination reactions. Have you guys seen a reaction like this before? Anywhere that you've encountered organic chemistry this semester, have you ever seen something like this? Anybody ever looked at our homepage? S-cis diene, dienophile with 2 electron withdrawing groups. intramolecular Diels-Alder creates a six-membered ring, but in this case it actually closes in on itself and creates this kind of small molecule box with this inner cavity inside of this hexagonal cube type structure. This doesn't exist. I made it up. But it's a very interesting example of an intramolecular Diels-Alder reaction. And there's another chemistry faculty here who said, oh, you should synthesize that. I'm not interested in it, but if you are, have at it. You have all the skills needed now to make a compound like that. All of the reactions that are needed, you can do in OChem 1. You can make carbonyls from alkenes or alkynes. You know how to make alkenes. You know how to make rings, especially six-membered rings, because you have the Diels-Alder reaction. So I've been waiting to show that to you all semester long, and now that I've finished providing all of our lecture material, I've done it. Sorry it took so long. And I've taken you guys over, so I apologize. Thank you for your time. Good luck on your unit tests this weekend. Mechanisms on SN1, E1, SN2, E2. And some short multi-step synthesis to do. Next week, 2 days of review before we come in to take our final exam. Come with questions. Have a good weekend.
Yeah, I think we go on Monday, right?